Hi, my name is Howard Green, and I'll be hosting this webinar. Today, we're very fortunate to be hearing from Joseph Koa. He's a senior staff engineer at Azul Systems. Joe's talk today is all about Zing Vision and how you can use it to identify and fix your most stubborn Java production issues. Just wanted to have everyone be aware this webinar is being recorded. If you have any issues or any questions, please either use the Q&A panel on your WebEx console, or you can send an email direct to hgreen, just like the color, at azulsystems.com. Thank you all for joining us, and I'm now turning it over to Joseph.
All right, thank you very much, Howard. And as you know, most people, when they're developing Java applications or running Java applications in production, they frequently want to know what's going on internally inside that Java application. And there's not a lot of insight that you can get from tools unless usually you have a lot of overhead associated with the collection of the metrics that are required to answer the questions that you have about that application in the production environment. We have a tool that I use frequently to help diagnose problems in production environments. And it helps to answer the toughest questions that you have about what's going on with the Java application in your production environment. That tool is called Zing Vision, and the tool connects to the Zing virtual machine and allows you insight into the inner workings of both the JVM, including the memory and threads inside your running Java application, as well as the application threads, and allows you to answer questions immediately about, for example, where is the primary CPU consumer in terms of methods in my application, and how did I get to that method, and why am I consuming so much memory, and what types of objects are accumulating in my Java heap. We're going to look at details such as these and how Zing Vision will fit into your production environment, development environment, or your test environment. We'll review the key features of the tool, see how it works, and we'll also look at another tool that's associated with Zing Vision that allows you to collect large amounts of information, the same type of information that you collect in Zing Vision, but to do that in a monitoring fashion. So what is Zing Vision? For you, what you'll see is Zing Vision is a browser-based visual window into your Zing VM. The interface presents itself as a hyperlink display that allows you to easily drill down and answer questions, as we'll see in the subsequent slides. The information provided is both the JVM internal and Java program information, and there's no additional performance overhead that's associated with connecting to the Zing VM, primarily because a lot of the collection of the metrics goes on in a normal fashion as you're running the VM. So you can connect and then just get a snapshot of what is going on at any time as the Zing VM is running. There's nothing special to install or configure. There's no monitoring console. And it's easy to get started as a user because you are just connecting using a browser. As I mentioned, the ZV Robot is a tool that collects and stores monitoring data, and remarkably we'll see that the collected data is the same as the Z Vision data. So here's an example of a Zing Vision deployment. Of note is the red box with Zing VM, and that communicates via HTTP to a Zing Vision server. That, in turn, you can connect to with your browser on the left-hand side through HTTP to the Zing Vision server. You need to start one Zing Vision server, and you can start that anywhere, and that Zing Vision server can connect to multiple Zing VMs, and likewise, you can connect with multiple browsers to the Zing Vision server. Zing Vision is really designed for safe use on production systems. Most tools are suitable for developers, but they're usually too heavy for production environments. They use JVM TI, BCI, or other special means of trying to collect information. but generally there's a substantial amount of overhead associated with the instrumentation required to collect the metrics. In order to minimize that overhead, frequently what you need to do is cut back on the features that you're actually able to use in the tools. And also, because of the substantial amount of configuration, it's frequently not practical for operation teams to use those tools when they most need them, when there's a critical problem in production. Zing Vision, on the other hand, is an ideal tool to use when you have a problem in a production environment. One of our users has a quote here that he considers it a flashlight in a dark place. It's integrated with a JVM, so it won't add overhead or perturb the running Java program. And it's meant to be used so that you can explore what's going on inside your running Java virtual machine and application. Also, by allowing you to run anytime, you can familiarize yourself with what's normal behavior so that when there is some sort of aberrant behavior that occurs, you're able to differentiate what you normally see inside the application from what is occurring during that phase when it's not running well. The key features of Zing Vision are, we'll start in the JVM where we actually are collecting the metrics, and that's the tick profiler. We'll also look at thread level views, lock contention view, the garbage collection views, and the Java heap object views, including live objects in the Java heap and object types that increase in number as the application runs. For the tick profiler, the goal really is to find hot methods, those methods that are consuming the most CPU time. Approaches used by other profiling tools include method tracing or bytecode instrumentation. The process of trying to figure out where the problem is in the application or where the high CPU consumers are is frequently an ongoing process where you selectively try to isolate those portions of the application that are having problems. The drawback is that you really need to know, or at least have some idea, where in the application the performance bottleneck occurs. Zing Vision uses thread runtime sampling to get around the problem of having to instrument the application. These are just fast snapshots of the code running in the Java execution threads, and we'll see how that's done in the next slide. This identifies quickly where the work is done in the application, and it's lightweight, and the metric collection is always on, even when you're not looking at the generated metrics. There's also a large amount of detail associated with the metrics that are collected, so you're able to go down to an instruction level granularity, which we'll see in the subsequent slides. The tick profiler works by interrupting each of the individual threads as it's running. Number one, it registers a signal handler. Then the thread runs, the kernel delivers a sig61. The thread is then interrupted on its normal stack, and the signal handler runs and creates a new youngest profiler. The data structure here, represented below, is the tick profiler conveyor belt that has a fixed number of positions per profile. When that new youngest profile is added, the oldest profile drops off. Therefore, Zing Vision is always showing you the most recent data for your application. For Zing Vision, what it does is takes a snapshot, aggregating all of the tick information that's on that conveyor belt into a timer tick profiler view. So let's now look and see what we're actually seeing. And here in a web browser is our window into the running Java virtual machine and displays the tick profiler page. At the top, you see the tabs, the overview, the Azul support, threads, CPU memory, compilers, and applications tabs, as well as information at the top saying the username, the host, and the PID, the version of the JVM that you're running, and the uptime for the process. Let's look more closely at what's going on in the timer tick profiler tab. And we have sub-tabs that are tick profile, meta-ticks, and event tracker. We have controllers for tick profiling. We can pause, reset, or stop tick profiling. And as well, we have filters that allow you to selectively look at individual threads, for example, in the filters, or specify the cutoff for the number of ticks that you're interested in. On the right hand here, we have, on the bottom, we have the percent, the ticks, and the source of those, which is the method in which the ticks have been collected. And here we see them sorted in decreasing percentage or number of ticks that have been accumulated in each of those methods. We can now next select a link to see the details. So we're going to look at from UTF and see what's going on internally in that. And now we get down and we see the C2 compiled JDK and application code for that individual method. Also, we see here across the top panel the percent, ticks, address, and code, and we're able to look at ticks for each of the individual instructions. So now you can not only isolate what method is the issue, but also what individual instructions or block of instructions within that method are the ones that are consuming the most CPU time. We also have the ability to answer another question, and that is, now I know where my hot method is, but what are the paths that were used to get to that hot method? And we use the callee, select callee, and now we can answer the question, how did I get to this method that's consuming so much CPU time? These are listed as call trees, and what you see here is they're sorted based on the highest CPU consumers, and you have two ways here from these top of stacks, 1 and 2 here, that show you how to get to the method, which is our from UTF method, which is the method that we were interested in. Likewise, you can go down the other more frequently taken chain that runs through this call chain to get to the same method. It also annotates both the percentages and the total number of ticks. This represents 33% of the ticks, and it was the major path to get to this, and there are other ways to also get to this particular method. We've now looked at how you can figure out where you can get information about where the most frequently executed methods are and those that are consuming the most CPU time. The next question you might have is, what exactly is going on inside my application in terms of the threads executing my application? How many threads do I have? What are they doing? What are their states? And what are their CPU consumption as well? Then you also might want to look at the housekeeping threads for the JVM, as well as examine an individual thread object to see what that thread object is. Then look at what for each of the individual threads are doing, and rather than the global view that you get that we just looked at from the entire process, look at what each individual thread is doing in terms of its stack traces and profile information. And finally, the question that many people have is, if the application is running slowly or there might be a problem, is there anything that's stalling my application, for example, lock contention? First of all, let's look at a novel way that the Zing VM uses to actually collect information about thread stacks. So if you're collecting thread stacks normally in the other JVMs that are available, what they will do is send a signal to all the threads to please come to a safe point. At that safe point, then they will start to collect the stack traces for each of the individual threads, represented by that white space between. But in this particular case, thread 3 didn't immediately come to a safe point. And the black times, the black bars for threads 1, 2, 4, and 5 represent times that the thread could have been doing work but wasn't doing work because it was waiting for thread 3 to come to a standstill. In the Zing Vision method, you get a request for the thread stacks, but rather than stalling all the threads, the Zing VM just stalls each individual thread, has that come to a safe point, then collects the stack information, moves on to the next thread, thread 2, 3, 4, 5. Those are all done in sequence. So no thread is required to wait for all of the other threads to come to a safe point, thereby lowering the overhead required to do these types of stack traces. In Zing Vision, this is the display. We have the Threads tab here visible, and underneath that, we have the list of threads, the stack traces, deadlocks, and contention. So let's first of all look at this. which is the threads list. What we see here are filters and control. So we can look at, for example, what I've selected here, which is all the threads running in the application. We have on the left the name of the thread, the state of that thread, whether it's running in I/O waiting on a monitor, or just waiting on a semaphore. And on the right-hand side, we have details that you can click through to get additional information. And this is the stack and the tick profiling. So let's select a link to see the stack traces for this first thread, the benchmark thread compiler 1. And what we see is a full stack trace, and there are threads here, the thread CPU time consumed for this particular thread, as well as we have 2 modes for details. This is the low mode. There's also a high mode that gives additional information about what's going on with the individual threads. And for those stack frames, we also have each of the frames information about the name of the method, the name of the file where that method occurs, and importantly, whether that method is being run as an interpreted method or a compiled method. This is important because if you have a slowdown and you see that you're running an interpreted method rather than a compiled method, you can immediately try to figure out why that method is not being compiled. So now let's look and select this link. Because this is a hyperlinked environment, we can select a link to see the details of our thread object. Here what we see are the value of the object's fields. We have the access, the name across the top, the type of that, and the value. And here what we can see is the name of the actual thread as the one that we had selected originally. So what we've been able to do is now see that we can get a lot of details about what's going on internally in the inner workings of the JVM and your application, allowing you to identify the profiles and stack traces and get a good idea of what work is going on inside your Java application. We can also look at the tick profile of the stack trace, and now we select the tick profile, and now we get the profile for an individual thread. This individual thread, again, looks a lot like the CPU consumption for the overall process, with our from UTF method, again, being the top consumer, other than the new stub, which is actually creating new objects. There's also lock acquisition that you might be interested in monitoring, particularly if the application is having some performance problems, and just looking at a normal application in production as well. Here what we see is in another application that's running, one that particularly has a lot of lock contention to show an example. What we have here is the blocking count for the locks, and we have 1,937 blocking acquisitions that we've recorded. The max is 14 seconds long, and the total accumulated time for blocking in this application is 8,384 seconds. So a particularly bad application, but a good example of showing you what to look for inside your application should you have any sort of lock contention. You can also then select the link to see details, and the details that we're going to try to address here is answering the question, how did I get to the contended lock in my code? And these are the call trees that allow you to actually identify where in your application the lock contention occurs, the specific method. That allows you to go through and quickly identify those areas where there is lock contention in the application. Down at the bottom, there's also a presentation of the summary metrics again for that lock. So now what we've seen is not only that we can get a lot of detail about what's going on in the application in terms of the threads, stack traces, and the profiling for the hottest methods in individual threads, as well as the overall CPU time consumed by the threads, but we're also able to look at the lock contention fairly easily in the running process. The next major area that you probably have questions about is memory. What's going on with the Java memory in the system? What's the collector doing? How much memory is the application using? And what types of objects are involved in occupying all of the memory that's used by the application? And if you're seeing through other monitoring that the size of the heap is increasing, then you might want to also look at identifying which object types are increasing in number. To do this, we go to the Memory tab, and the Memory tab has a summary, a GC summary, GC history. You can browse objects, look at live objects, and look at type velocity, which is a description of the objects that are increasing in number or occupying more memory in the Java heap over time. The Java heap overview in this memory summary gives you information about the amount of memory requested at the VM launch, the application heap size, the application heap used, the code cache used, and the collection count. So an overview of what your application memory is profiled as, and as well then details about individual areas. Here is below the process's Zing memory, which is used for the Java heap, and Java system, Java heap, Java pause prevention, and the total amount of memory. And then Linux memory, the amount available on the system, both used, free, and total. And then finally, down at the very bottom, the amount of process memory, the Linux memory used by the Java process. So this will be able to quickly help you to identify any problems that you might have, particularly if you take snapshots of the process over time. You'll be able to see which of these areas are increasing over time. There's also a great deal of details about the individual collections, and we keep a view at the bottom of this panel, which is the GC history of the last 50 garbage collections. This gives you the maximum, the peak, the used, and a lot of details about, for example, garbage, the pages of memory used, and then the allocation rates both between garbage collections and when you're doing a garbage collections. Another important area that we keep track of is in this far right column is application threads. We keep a track of not only the application threads, but those that are delayed as a result of not being able to make forward progress because they can't make an object allocation. That's important because those threads are really blocked and are most usually associated with heap sizes that are too small. At the top of the panel, we have a view, a graph, and that graph shows the number of metrics over time. Switching, we can also look at the collection summary, and this memory summary is a summary that is the average of the metrics over time from the previous panel. And what you see here is, for example, the amount of garbage found in each of the garbage collections. You see the mean here is 6 gigabytes, and 3 gigabytes is the standard deviation for each of those. We now switched over and we're looking at the live objects here, and the memory tab, the live objects. And we can look at the objects that are in the old generation. This does require turning on a JVM option in order to collect this information. And this information describes a class name for the object type, then the count, the size in bytes, the average size is the total size in bytes, the average size, and then the percentage of the live set that this particular type represents in the total memory. This is sorted, and it's sorted on the sum of the size of each of the objects of that type. And that would be this column right here, the third column that we have right here, and it's the sorting. You can also over here expand, and I've done this in this particular slide, and show you the types with the references to objects of that type. So this will answer your question of not only what objects are in the heap, but also what are the references that are holding each of those individual types of objects. And we can then look and see which of those objects or which of those references are holding most of those objects. And for this particular case, it's the Java NIO heap char buffer R, which is holding the bulk, 67% of that 22% of the total char arrays that are occupying the most space in the application. You might also be interested, as I mentioned earlier, if you know that the size of the heap is increasing, the number of live objects is increasing over time, then you might want to know, well, what type is accumulating in my Java heap? And in order to answer that question, we have what I mentioned earlier, the type velocity. These are the object types with increasing memory consumption in the old generation. And this, again, this is our object array that's increasing in size. And we see the latest count, latest size, prior count, the prior size, the delta count, the delta size, and the growth rate. So you can see these are, again, the sorted based on the growth rate decreasing over time. So here we have the total, which is the amount total that's the growth size, and here we have the JavaLang object, which is predominantly increasing in size. There's also a selectable time interval, so if you're interested in selecting a short time or a longer period of time, you can then look to see whether or not those differ over time. That concludes our look at the memory area, and we've been able to answer a lot of the questions that we posed at the beginning about what was going on with your Java heap. With being able to identify the objects, the types of collections, being able to see details about the collection, and then also being able to look down and look at the actual objects in the heap and identify those types of objects which are increasing rapidly in size or occupy more of the heap space. The next area that we're going to cover is the ZV Robot, and we've mentioned ZV Robot previously. And ZV Robot connects using HTTP, and it's a running process that you simply start on either the Linux host where the Zing VM is running or on an additional Linux host. In this case, I've started on another host connected through HTTP to the Zing VM. And you configure the ZV Robot through a properties file. It's a Java program. And then it, at the interval that you specify, in this case usually 1 minute by default, it collects information. And those pages, those white pages that we see that are being collected here, are able to be viewed in a browser. Those are XML pages that then have SSLT assists that are associated with them to display the XML information in your browser. And as I mentioned earlier, there's really no difference between the information that you see there that's collected and the information that we just reviewed when we went through the slides for Zing Vision. In fact, many times when people are using this and I'm working with them, they're frequently at some point a little bit confused because the view is so realistic that they want to click the hyperlinks, even though these are simply pages that have been collected by ZV Robot. So that concludes the discussion of the Zing Vision. And if you want to try Zing Vision, you can request a trial copy of Zing at that URL that's displayed there, and then download and run Azul Inspector to check your system. You can then download and install Zing, which includes Zing Vision and ZV Robot, run your application, and then observe your application of the JVM's activity using Zing Vision. So now we're at the questions period, and if you have any questions, please let me know. We have a couple of questions already that have come in, and the first question is, what is the overhead of collecting additional data? And the overhead for collecting additional data, as we've seen, is very low and unnoticeable because of the tick profile being on and collecting information. So it's merely a scan over the array of tick profiles that we have in the JVM, aggregating that data, and then pushing it out as an XML document. That's fairly lightweight. You probably won't notice that in most environments. There are additional overheads. For example, There is a slight amount of overhead for collecting the memory information. That does require that you turn on an option in order to collect that information. The thread stack traces, we've gone over how we minimize the cost for those thread stack traces by not stopping the whole application to do the stack tracing. And that collection is fairly fast, and we have actually isolated the amount of time it takes to collect the header information separately from the amount of time that it takes to collect the actual stack traces and walk the stacks. If you have many stack traces to collect in the application, you have lots of threads, then the overhead for that can be fairly high because you are having to query, for example, 300 threads. The other types of data, usually it's fairly low overhead. There's not much noticeable that I've seen, certainly in most environments. The other question that came in is, how do I turn on additional collection? The only thing that we mentioned here was we did have to have an option to the JVM in order to turn on the memory collection, additional collection of memory information concerning the live objects and the type velocity. The JVM itself does require that you specify the port with which you want to connect when you initially start, and that's the only change that you really have to make to your application. You just set it up with an option called -XX:\ARTA port, and then specify the port that you want to use to connect to that particular JVM instance. Are there other questions? All right. Well, if there are no other questions, thank you for attending, and certainly I'll go back to the previous slide where you can get information about Zing Vision, and we look forward to your interactions with the Zing VM and any additional questions and input that you might have into Zing Vision. Thank you very much.
Great, thank you all. As we noted at the beginning, this is being recorded. You'll see a link to the webinar recording on our website, we hope, later today. Thanks again, and enjoy your weekend. Take care.